Now we are going to discuss highway materials, and we will mainly focus on aggregates and the bituminous materials in this course of transportation engineering. We have already discussed soils in detail in the subjects of Geotechnical Engineering 1 and Geotechnical Engineering 2. So we are going to focus on aggregates and the bituminous materials. Aggregates. The term aggregate refers to granular mineral particles that are widely used for highway bases, subbases, and backfill. Aggregates are also used in combination with the cementing material to form concretes for bases, subbases, wearing surface, and drainage structures. Sources of aggregates include natural deposits of sand and gravel, pulverized concrete and asphalt pavements, crushed stone, and blast furnace slag. Properties of aggregates. The most important properties of aggregates used for highway construction are particle size and gradation, hardness or resistance to wear, durability or resistance to weathering, specific gravity and absorption, chemical stability, particle shape and surface texture. Aggregate should be free from deleterious particles or substances. First, look at the particle size and gradation of aggregates. A key property of aggregates used for highway bases and surfaces is the distribution of particle sizes in the aggregate mix. The gradation of aggregates, that is the blend of particle sizes in the mix, affects the density, strength, and economy of the pavement structure. A grain size analysis is used to determine the relative proportions of various particle sizes in a mineral aggregate mix. The grain size analysis data are usually plotted on an aggregate grading chart, as shown in the figure on the next slide. With the aid of such a chart, engineers determine a preferred aggregate gradation and require that the gradation of aggregate used for highway projects conform to the limits of a specification band. Now here you can see the aggregate gradation specification chart. Now here you can see that this is the gradation of the aggregate, given aggregate, and we are having the upper limit of specification, this one, and this is the lower limit of this specification. So the aggregate that we are going to use in the highway that must be in this region, that is the region between the upper limit and the lower limit. Testing sieves commonly used for highway projects are those with 2.5, 2, 1.5, 1, 3/4, 1/2, and 3/8 inch square opening for the large size fractions, and those with 4, 8, 16, 30, 50, 100, 200 meshes per inch for the smaller fractions. The later sieves are designated as number 4, number 10, and so on. Then look at the resistance to wear. Materials used in highway pavements should be hard and resist wear due to the loading from compaction equipments, the polishing effect of traffic, and the internal abrasive effect of repeated loadings. The most commonly accepted measure of the hardness of aggregates is the Los Angeles abrasion test. The machine used in the Los Angeles abrasion test consists of a hollow steel cylinder closed at both ends and mounted on shafts in a horizontal position. Now here you can see the Los Angeles abrasion testing machine. So this is the cylinder, and we can place the aggregate along with the steel balls in this, and then this drum will be rotated like this. A removable steel shelf extending the length of the cylinder is mounted on the interior surface of the cylinder. To perform the Los Angeles abrasion test, a clean sample of the aggregate to be tested is placed in the cylinder, along with the standard weight of steel spheres or balls as an abrasive charges. The drum is then rotated at a speed of 30 to 33 revolutions per minute for 500 revolutions, after which the aggregate sample is removed and sieved on a number 12 sieve. The material retained on the sieve is washed, dried to a constant mass, and weighed. The difference between the original mass and the final mass of the sample, expressed as a percentage of the original mass, is reported as the percentage of wear. A detailed procedure for this test is given in AASHTO method T96. Then comes durability or resistance to weathering. The durability of aggregates is commonly measured by a soundness test, as described in AASHTO method T104. This test measures the resistance of aggregates to disintegration in a saturated solution of sodium or magnesium sulfate. It simulates the weathering of aggregates that occur in nature. The test is made by immersing sized fractions of the aggregate to be tested in a saturated solution of sodium or magnesium sulfate. The aggregate is then removed and dried in an oven to a constant mass. This process is repeated for a specified number of cycles, typically 5. So typically 5 cycles are used. After the repeated cycle of alternate wetting and drying, the aggregate is divided into fractions by sieving, and the percentage weight loss is determined for each fraction. Okay, now the specific gravity and absorption. Here the absorption means the water absorption. The specific gravity and absorption of aggregates are important properties that are required for the design of concrete and the bituminous mixes. The specific gravity of a solid is the ratio of its mass to that of an equal volume of distilled water at a specified temperature. Because aggregates may contain water-permeable voids, two measures of specific gravity of aggregates are generally used: apparent specific gravity and bulk specific gravity. So this point is very, very important, that aggregates may contain water permeable voids. So two measures of specific gravity of aggregates are generally used. One is the apparent specific gravity, the other is the bulk specific gravity. Apparent specific gravity is denoted by G sub A, is computed on the basis of the net volume of the aggregate, that is the volume excluding the water permeable voids. So G sub A, that is equal to M sub D divided by V sub N divided by the density of water. So here V sub N, if you just look at that, this is the net volume of the aggregate, that is the volume excluding the water permeable voids. So again, you can see the formula over here on this slide, and you can see that M sub D means the dry mass of the aggregate. V sub N is the net volume of the aggregate. That means we are going to exclude the volume of the absorbed water or the water permeable voids. So keep this thing in the mind that the volume of absorbed water is equal to the volume of water permeable voids, and rho sub W, that is the density of water. The bulk specific gravity, it may be denoted by G sub B, is computed on the basis of the total volume of the aggregates including the water permeable void. So here we are going to consider the total volume, that is the bulk volume you can say, and obviously we are going to include the water permeable voids. So this is the formula. G sub B is equal to M sub D over V sub B over rho W. And here keep this thing in the mind that V sub B, that is the total volume of the aggregates including the volume of absorbed water. And I have already mentioned that the volume of absorbed water means the volume of the water permeable voids. Well, this point is very important. The difference between the apparent and bulk specific gravity accounts for the water permeable voids of the aggregates. So I will repeat this thing, that the difference between the apparent and bulk specific gravities accounts for the water permeable voids of the aggregates. One can measure the volume of such voids by weighing the aggregates dry and in a saturated surface dry condition, that is with all permeable voids filled with water. So I will repeat this thing, that one can measure the volume of such voids by weighing the aggregates dry and in a saturated surface dry condition, that is with all permeable voids filled with water. The difference between the two masses is the mass of the absorbed water, M sub W. The absorption of water is usually expressed as a percentage of the mass of the dry aggregate. Okay, to get the weight of saturated surface dry aggregate, what we do, we just immerse the aggregate in water for an appreciable period of time, generally 24 hours, and then you can take out that aggregate from the water container, and then you can use some water absorbing cloth or some sort of towel upon the surface of the particles, and in this way you will be getting the saturated surface dry condition. Now on this particular slide you can see the percentage water absorption formula, M sub W divided by M sub D into 100. Now just to give you the real feel about the apparent and the bulk specific gravity, look at this problem. The statement, the dry mass of a sample of aggregates is 1982 grams. The mass in a saturated surface dry condition is 2006.7 grams. The net volume of the aggregate is 734.4 cubic centimeter. Find the apparent specific gravity, the bulk specific gravity, and the percentage absorption. Now look at the solution. So obviously from the given information you can get this thing, that the mass of absorbed water is 2006.7 minus 1982, and it comes equal to 24.7 grams. Now the volume of the absorbed water, it can be determined uh, by using this concept that 24.7 divided by 1, this is the density of the water. So basically we have used the formula of the density over here. You know the density of water is obviously equal to the mass of water divided by volume of water. So we have used that concept. So obviously the volume of absorbed water coming equal to 24.7 cubic centimeter. So obviously the bulk volume will be 734.3 plus 24.7. So this way you will be getting the bulk volume. So first you can calculate the apparent specific gravity, and you know in the apparent specific gravity the net volume is to be considered. So you can see 1982 divided by 734.4, this is the net volume, and in the denominator we are having the density of water, so it is coming equal to 2.699. Now on this slide you can see the bulk specific gravity, and you can see here we are using the bulk volume, that is 759.1, and you are getting G sub B equal to 2.611. And then by using the formula of the percentage water absorption, so you can get this answer, that is 1.25%. So in this way, in this problem, we determine the apparent specific gravity, bulk specific gravity, and the percentage water absorption. Okay, now chemical stability of aggregates. Certain aggregates may be unsuitable for a particular highway construction application because of the chemical composition of the aggregate particles. In asphalt mixes, certain aggregates that have an excessive affinity for water may contribute to what is known as film stripping, leading to disintegration of asphalt concrete. So in film stripping, what happens, the bond between the asphalt and the surface, that vanishes. So that is called as the film stripping. So this point is very important, and I will repeat that in asphalt mixes, certain aggregates that have an excessive affinity for water may contribute to what is known as film stripping, leading to disintegration of asphalt concrete. An aggregate that is hydrophobic in nature may be said to be one which exhibits a high degree of resistance to film stripping in the presence of water. So obviously hydrophobic aggregates are good aggregates. The bituminous substance in a bituminous mixture may generally be assumed to be present in the form of thin films surrounding the aggregate particles and filling or partially filling the void spaces between adjacent particles. These thin films of bituminous material adhere to the surface of normal aggregates and contribute to the shearing resistance of the mixture, this effect being generally considered as a part of the cohesion of the mix. So we use the term cohesion. On continued exposure to water, either in the laboratory or in the field, the bituminous mixtures containing certain aggregates show a definite tendency to lose shearing resistance or strength because of decrease in cohesion, primarily due to replacement of the bituminous films surrounding the aggregate particles with similar films of water. So the aggregates that exhibit this tendency to a marked detrimental degree are termed hydrophilic aggregates. Hydrophilic meaning water-loving. Conversely, aggregates that show little or no decrease in strength due to film stripping are called hydrophobic or water-hating. In judging the relative resistance to film stripping of aggregates, several different laboratory procedures have been used, including various immersion stripping tests such as ASTM D1664 static immersion test and various immersion mechanical tests such as ASTM D1075 immersion compression test. Now, some other properties of aggregates. Specifications for aggregates used in highway construction commonly have requirements related to the particle shape, surface texture, and cleanliness of the aggregate. Specifications for aggregates used in bituminous mixes usually require that the aggregates be clean, tough, durable in nature, and free of excessive amounts of flat or elongated pieces, dust, clay balls, and other objectionable material. Now, if you just look at this table, descriptive evaluations of mineral aggregates. So first you can see the particle shape, and here you can see that the description about the different types of particle shapes is given. So rounded particles, irregular particles, flaky particles. Flaky particles are those particles in which the thickness is very small. Angular particles, elongated particles. Elongated particles are those particles in which the length is dominant and the other dimensions are very small. So flaky and elongated. So these are the different shapes. And you can see here the description is given and then examples are mentioned. And if you just look at this second part, part B, surface texture, and here you can see the glossy, smooth, granular, rough, crystalline, honeycombed, and porous. So these are the different surface textures which have been discussed in this table. Okay, now we will discuss the sand equivalent test. That is also very important for the fine aggregate. Basically, a measured volume of fine aggregate and a small quantity of flocculating solution are poured into a graduated plastic cylinder and are agitated to loosen the clay-like coatings from the sand particles in the test specimen. The specimen is then irrigated using additional flocculating solution, forcing the clay-like material into suspension above the sand. After a prescribed sedimentation period, the height of the flocculated clay is read and the height of the sand in the cylinder is determined. The sand equivalent is the ratio of the height of the sand to the height of the clay times 100. So I will repeat that the sand equivalent is the ratio of the height of sand to the height of clay times 100. So there are two important points which are mentioned. This test assigns an empirical value to the relative amount, fineness and character of clay-like material present in the test specimen. A minimum sand equivalent value may be specified to limit the permissible quantity of clay-like fines in an aggregate. Granular subbase. Description. This item shall consist of furnishing spreading in one or more layers, and compacting granular subbase according to the specifications and the drawings and or as directed by the engineer. Material requirements. Granular subbase material shall consist of natural or processed aggregates such as gravel, sand, or stone fragment, and shall be clean and free from dirt, organic matter, and other deleterious substances, and shall be of such nature that it can be compacted readily under watering and rolling to form a firm, stable subbase. The material shall comply with the following grading and quality requirements. So, for the subbase material, two gradings are specified, grading A and B, and here you can see that the coefficient of uniformity, that is D60 over D10, is mentioned, and it shall be not less than 3. So that is the requirement for the subbase material. The subbase material shall have a gradation curve within the limits for grading B given. However, grading may be allowed by the engineer in special circumstances. So basically, the availability of the material that will dictate you in this regard. The material shall have a CBR value of at least 50% determined according to H2T 193. The CBR value shall be obtained at a density corresponding to 98% of the maximum dry density determined according to H2T 180. So you know the CBR stands for California Bearing Ratio. It is a penetration test. So at least 50% value is required for subbase material. The coarse aggregate material retained on sieve number 4 shall have a percentage of wear by the Los Angeles abrasion of not more than 50%. Well, keep this in the mind that smaller the value of Los Angeles abrasion value, better is the material. So the requirement for the subbase material is that Los Angeles abrasion value should not be more than 50%. It should not be more than 50%. In order to avoid intrusion of silty and clay material from the subgrade in the subbase, the ratio D15 of subbase divided by D85 of subgrade shall be less than 5. So that is another requirement for the subbase material. Now here D sub 85, D and D sub 15 are the particle diameters corresponding to 85% and 15% respectively, passing by weight in a grain size analysis. I'm sure you have used D10, D30 and D60 in the geotechnical engineering 1 and during the sieve analysis. So the same concept can be used over here, but it is corresponding to 85% passing and it is corresponding to 15% passing. The fraction passing the 0.075 millimeter, that is the opening size of the sieve number 200, sieve shall not be greater than 2/3 of the fraction passing the 0.425 millimeter, that is number 40C. The fraction passing the 0.425 millimeter sieve shall have a liquid limit of not greater than 25% and a plasticity index of 6 or less. If oversize is encountered, screening of material at source shall invariably be done. No hand picking shall be allowed. However, hand picking may be allowed by the engineer if oversized quantity is less than 5% of the total mass. Sand equivalent for all classes shall be 25% minimum. So these are the requirements uh, which have been recommended by AASHTO for sub-base material. Now we have reached here, that is crushed aggregate base course, and we are going to discuss the different requirements, the different requirements that must be fulfilled by the aggregate that is to be used as the base material, base course. This item shall consist of furnishing, spreading, and compacting one or more layers of crushed aggregate base course on a prepared subgrade, subbase, or existing road surface in accordance with the specifications and the drawings and or as directed by the engineers. Material requirements. Material for crushed aggregate base course shall consist of crushed hard durable gravel, rock or stone fragments. It shall be clean and free from organic matter, lumps of clay, and other deleterious substances. The material shall be of such a nature that it can be compacted readily under watering and rolling to form a firm, stable base for both flexible and rigid pavements. The crushed aggregate base course shall comply with the following grading and quality requirements. So here again you can see that two types of gradings are there, grading A and grading B. So grading requirements for aggregate based material, and look at this thing, this is very important. The material shall be well graded such that the coefficient of uniformity D60 or D10 shall be greater than 4. The gradation curve of the material shall be smooth and within the envelope limits for grading A or B given. Crushed aggregate material retained on sheet number 4 shall consist of material of which at least 90% by weight shall be crushed particles having a minimum of 2 fractured faces. The coarse aggregate shall have a percentage of wear by the Los Angeles abrasion test of not more than 40. So you can see here we are having a strict criteria that you can see that the Los Angeles abrasion test value should not be more than 40 in the case of base coarse material. The material shall have a loss of less than 12% when subjected to 5 cycles of sodium sulfate soundness test according to AASHTO T104. The sand equivalent determined according to AASHTO T176 shall not be less than 45, and the portion of filler including any blended material passing number 40 mesh sieve shall have a liquid limit not more than 25 and a plasticity index not more than 4 when tested in accordance with AASHTO T89 and T90. The material passing the 19 mm sieve shall have a CBR value of minimum 80%. Tested according to AASHTO T193, the CBR value shall be obtained at the maximum dry density determined according to AASHTO T180 method D. Laminated material shall not exceed 15% of total volume of crushed aggregate base course. So you have seen that in the case of base course material, we are having very strict criteria, and all these requirements must be fulfilled. Otherwise, you cannot use, you cannot recommend that particular material to be used as base course material. Okay, now look at filler or filler for blending. A filler, in addition to the naturally present in the crushed aggregate base course material, is necessary for meeting the grading requirements or for satisfactory bonding of the material. It shall be uniformly blended with the base course material at the crushing plant or in a pug mill until otherwise approved. The material for such purpose shall be obtained from sources approved by the engineer. The material shall be free from organic matter, dirt, shale, clay and clay lump or other deleterious matter and shall conform the following requirements. So these requirements have to be fulfilled. So you can see the percentage passing by weight corresponding to these sieves, the plasticity index and the sand equivalent values requirement. However, the combined aggregate prepared by mixing the coarse material and filler shall satisfy the requirements as mentioned above. So it is clearly mentioned that these requirements must be fulfilled. Okay, now we are going to discuss the bituminous materials. Bituminous materials are used extensively for roadway construction, primarily because of their excellent binding or cementing power and their waterproofing properties, as well as their relatively low cost. Bituminous materials consist primarily of bitumen, which according to ASTM D8 is a class of black or dark colored solid or viscous cementitious substances composed chiefly of high molecular weight hydrocarbons. By definition, it is soluble in carbon disulfide. Bituminous materials are divided into two broad categories: asphalts and tars. As far as the asphalts are concerned, asphalts are the residues of the petroleum oils. A great majority of asphalts used nowadays are the residues from the refinery of crude oils, although there are natural deposits called native asphalt. Now look at the tars. Tars are the residues from the destructive distillation of organic substances such as coal, wood, or petroleum. Tars obtained from the destructive distillation are crude tars, which must undergo further refinement to become raw tars. Now look at some unique properties associated with the asphalts and the tar. Asphalts have no odor, are more resistant to weathering, and less susceptible to temperature than tars, which have a pungent, creosote-like odor and react to weathering and temperature. Asphalt can be dissolved in petroleum oils, whereas tars cannot. Therefore, tars have been used to seal asphalt concrete surfaces, such as fog seals, to improve the oil resistance of asphalt surfaces. Asphalts are black in color, whereas tars are usually brown-black in color. Today, tars are not used extensively as binders for highway pavements. Now look at the sources of asphalts. Number one, petroleum asphalts or penetration grade refinery bitumens. Bitumen that are produced artificially from petroleum crudes, usually naphthenic and asphaltic based crudes, are known as refinery bitumens. second source, that is the natural asphalt, and it includes the following: lake asphalt and the rock asphalt. So first look at the lake asphalt. The largest natural deposit of lake asphalt occurs on the island of Trinidad off the northwest coast of South America. The main lake of asphalt covers an area of roughly 35 hectares, has the depth of about 90 meters, and is estimated to contain 10 to 15 million tons of material. Following excavation, the asphalt is heated to 160 degrees Celsius to drive out gases and moisture, and then run through strainers to remove vegetable debris before being poured into wooden barrels for export under the name of Trinidad Impure or refined Trinidad Lake asphalt. The refined lake asphalt product typically contains about 55% bitumen, 35% mineral matter, and 10% organic matter. Following the first commercial shipment to England in 1840, it was widely used in road construction until the introduction of pitch bitumen in the 1960s. That is a blend of 70 to 80% of bitumen with 20 to 25% coal tar pitch, which had similar qualities. Now look at this photograph digging at an asphalt lake. So this is the asphalt lake. And you can see this one, that is the Trinidad Lake asphalt. Now look at the natural rock asphalts. Natural rock asphalts are mainly limestones and sandstones that are saturated with typically 5 to 15% of natural bitumen. Historically, the natural rock asphalt used in the United Kingdom was imported from the Val de Travers region in Switzerland and from the Gard region in France. Their usage is covered by a British standard, but natural rock asphalts are rarely employed in road construction in the United Kingdom today. So here you can see the natural asphalt. Production of asphalt. As mentioned earlier, asphalts are the residues, byproducts of the refinery of petroleum oils. A wide variety of refinery processes such as straight distillation process, solvent de-asphalting process, and solvent extraction process may be used to produce asphalt of different consistency and other desirable properties. Depending on the sources and characteristics of the crude oils and on the properties of asphalt required, more than one processing method may be employed. Okay, now we are going to discuss the cutback asphalt. Asphalt cement produced from the vacuum steam distillation exists as a semi-solid at room temperature, and usually a proper workability can be attained by heating the asphalt cement to a temperature of 120 degrees centigrade to 165 degrees centigrade to liquefy it. In order for asphalt products to attain workability at room temperature, they must be rendered liquid at room temperature. There are two ways to liquefy asphalt without resorting to heat. Dissolve the asphalt, cut in solvent, emulsify it in water. When volatile solvents are mixed with asphalt cement to make a liquid product, the mixture is called cutback asphalt. So I will repeat. When volatile solvents are mixed with asphalt cement to make a liquid product. The mixture is called cutback asphalt. After a cutback asphalt is exposed to air, the volatile solvent evaporates and the asphalt in the mixture regains its original characteristics, and that is termed as curing. So we can say it has been cured. Depending on the volatility of the solvent used, the rate of curing of cutback asphalt can vary from a few minutes to several days. Following are three types of cutback asphalt and the solvent used. Number one, rapid curing RC, and gasoline or naphtha is used in that case. Number two, medium curing MC, and the kerosene is to be used in that case. And the slow curing SC, the road oils are to be used. Cutback asphalt is commercially available in different grades. The suffix number, for example MC70, represents the minimum kinematic viscosity in centistrokes at 60 degrees centigrade for the particular grade. So here this 70 is basically representing the minimum kinematic viscosity in centistrokes at 60 degrees Celsius. Specifications for rapid curing, medium curing, and slow curing are given in ASTM D2026, D2027, and D2028 respectively. Cutback asphalt is increasingly being replaced by emulsified asphalt in the commercial use. Okay, now we are going to discuss emulsified asphalt. Emulsified asphalt is a mixture of asphalt cement. Well, keep this in the mind that we are using the word asphalt cement. This is simply bitumen, or you can say the asphalt, because it is having the binding material, so that's why the word cement is being used. So emulsified asphalt is a mixture of asphalt cement, water, and an emulsifying agent. These three constituents are fed simultaneously into a colloid mill to produce extremely small globules, 5 to 10 micrometer, of asphalt cement, which are suspended in water. The emulsified agent imparts electric charges, cationic or anionic, to the surface of the asphalt particles, which causes them to repel one another. Thus, the asphalt particles do not join into a single mass. The emulsified asphalt thus produced is quite stable and could have a shelf life of several months. When an emulsified asphalt is exposed to the air alone or mixed with an aggregate, it sets or breaks because the asphalt globules react with the surface they are in contact with and coalesce. That means just develop a collective mass, squeezing out the water between them. The evaporation of water is the primary mechanism that finally causes anionic emulsified asphalt to break or set. Electrochemical processes are the primary mechanism that cause the cationic emulsified asphalt to break. Emulsified asphalt offers certain advantages in construction, particularly when used with moist aggregate or in wet weather. An emulsified asphalt does not require a solvent to make it liquid and thus is relatively pollution-free. Because emulsified asphalt has low viscosity at the ambient temperature, it generally can be used without additional heat. These factors tend to make emulsified asphalt more energy efficient and less costly than cutback asphalt. Environmental factors. In areas where highly frost susceptible soils and severe low temperature conditions are encountered, it may be necessary to remove and replace soils susceptible to frost heave or take other precautions prior to pavement construction. In extremely hot climates, asphalt mixes should be designed to resist rutting and maintain stiffness at high temperature. Rutting is basically a defect in the pavement, and you can say because of the poor quality of the bitumen, sometimes we are having the continuous depression under the wheels of the vehicles on the road surface. So that is called as rutting. Because asphalt mixtures are influenced by temperature, it is recommended that different asphalt grades to be used where different temperature conditions prevail. So this point is very, very important, and I will repeat this. Because asphalt mixtures are influenced by temperature, with the increase of temperature, what would be the effect on the asphalt? It would become soft. Because asphalt mixtures are influenced by temperature, it is recommended that different asphalt grades be used where different temperature conditions prevail. Table on the next slide gives recommended asphalt grades for the various temperature conditions. So selecting asphalt grade. So here you can see that the three different conditions are highlighted: cold, warm, and hot. So cold condition means that mean annual air temperature is less than or equal to 7 degrees centigrade. Warm means that mean annual air temperature between 7 degrees Celsius and 24 degrees centigrade. And in hot case, the mean annual air temperature is more than 24 degrees centigrade. So look at the recommended asphalt. For cold condition, AC 10, AR 4000 and 80 to 100 penetration grade of bitumen. And for warm, AC 20, AR 8000 and 60 to 70 penetration grade bitumen. Here in the case of hot condition, corresponding to hot condition, the recommended asphalts are AC 40, AR 8000 and 40 to 50 penetration grade. Well, keep this in the mind that AC means asphalt cement and AR means aged residue, aged residue. And if you just look at this number which is mentioned here, this is basically the viscosity at 60 degrees centigrade in poise divided by 100. I will repeat, this number is basically representing the viscosity at 60 degrees centigrade in poise divided by 100. And if you just look at this one, AR 4000, so this number is simply representing the viscosity at 60 degrees centigrade in poise. Well, I will repeat. Here, in case of asphalt cement, the number which is there, this one, this is basically representing the viscosity at 60 degrees centigrade in poise divided by 100. But here this one, this number that is linked with AR, this is simply, you can say, the viscosity at 60 degrees centigrade in poise. And this one, 80 penetration reading minimum and the maximum penetration reading 100. And same concepts are valid for the other cases. Now, asphalt cement is the asphalt that you have got from some refinery or from some other source, Now how can you get AR? AR, the edged residue. To get the edged residue, we are having the two tests: thin film oven test and the rolling thin film oven test. And in those tests, we maintain 163 degrees centigrade temperature, and ultimately you will be able to get the edged residue. So for cold temperature condition, the recommended grades of bitumen, this one. For warm, we can use these bitumens or asphalt, and for hot condition we can use these bitumen. So in this way we have discussed the aggregates and the bituminous materials in this lecture. Thank you.